Hi, this is Calculus 12, Chapter 2.3, Part 2. We're going to be looking at continuous functions some more. Here's a definition. A function f is continuous on an interval if and only if, that's IFF, it is continuous at every point in the interval. And IFF, if and only if, is done with double arrows. A continuous function f is one that is continuous at every point in its domain. Its domain, that's the important part. It doesn't imply that it's continuous on all reals, it's only continuous on its domain. For example, y equals 1 over x squared is a continuous function because it is continuous on its domain. The domain is absolute value of x is greater than 0, even though it's not continuous on this interval. Another way to write this is x does not equal 0, or you can write x is less than 0 or x is greater than 0. Okay, so you have this condition or you have that condition. Okay, this interval includes 0, so that's why it's not part of the domain. This can also be written as this. Okay, so you might not be familiar with this notation. If it's round brackets, we take away the equal signs. If it's a square bracket, it's less than or equal, less than or equal. You can also have a square bracket on one side and a round bracket on the other side. Here's a theorem. Any polynomial is continuous on all reals. Another theorem, any rational function is continuous on its domain. That is, anywhere except at its NPVs. And here's another theorem. The following functions are continuous on their domains. An odd root, that's x is all reals. Even root, x is greater than or equal to 0. And again, I'm just going to reiterate this. Does not imply all reals. Trig, cosine and sine, all reals. Tangent, we can write it this way. X is all reals except x does not equal the asymptotes. Okay, so the asymptotes occur at all the odd pi over 2's. Inverse trig function. Normally written like this. This is less confusing because it doesn't look like a power. So it means inverse cosine. That's from -1 to 1. And we know this because the range of cosine is -1 to 1. So the inverse means that this is the domain. Sine, same thing, -1 to 1. The range of tangent is all reals, so the domain of inverse tangent is all reals. Exponential functions, all reals. Logs. The range of exponential functions is y is greater than 0, so the domain for logarithms must be x is greater than 0. And for the absolute value function, x is all reals as well. So we have properties of continuous functions. If f and g are continuous at a and c is a constant, then the following functions are also continuous at a. F plus g, f minus g, c times f, f times g. F divided by g, provided that g of a does not equal 0. Okay, so really we're talking about f of a plus g of a, f of a minus g of a, and so on. Okay, let's prove these. And recall that we only modify one side of the equation when we're doing a proof, and we show that it can be modified to equal the other side. If you're stuck, you can use reverse engineering to figure out the steps and then write it in reverse order. So let's look at the proof of f plus g. And we use some of our theorems. Since f and g are continuous, we know the limit as x approaches a of f of x equals f of a. Similarly, limit x approaches a, g of x equals g of a. Therefore, limit x approaches a, recall that this is a shorthand for f of x plus g of x. Okay, so the limit as x approaches a of f of x plus g of x. So we break up our limits using our limit properties. And we have f of a plus g of a, and that is f plus g of a. And we write QED, quad error demonstratum. Okay, so we have the limit equals the value. So it means it's continuous. And here's the proof of f times g. It's very similar. And you should do the proofs for f minus g and f divided by g on your own. And you should have something very similar. Try to not look at this when you're doing the proofs and then compare your answers. That way you'll check to see if you actually understand it. Okay, here's a harder theorem, composition of continuous functions. If g is continuous at a and f is continuous at g of a, then f of g is continuous at a. We're doing f of g of x. Okay, so we have to do limit x approaches a. So we're substituting an a inside here. So we're looking at g of a. Now we're just going to estimate. This is negative 1.5. So now we're at negative 1.5. So that's our answer. Okay, so that's why f is continuous at g of a. And then this is f of g of a. So composition is a little bit different than our other properties here. The proof is a little bit more difficult, and we're not going to be covering that. Okay, intermediate value theorem. Suppose that f is continuous on an interval a to b, a closed interval, and let n be any number between f of a and f of b, where f of a does not equal f of b, then there exists a number c such that it's in the open interval from a to b, such that f of c equals n. So when you're looking at a theorem like this, you work through an example, and then you go back and read this. That's the best way to get an understanding. So let's look at what it means. So here we have A, here we have B. This must be f of A, this must be f of B. So we need to draw a continuous function. It can go up and down as many times as it wants, but it has to be continuous. So we can't lift our pen. There's no jump discontinuities. There's no discontinuities of any kind. So we can draw it below f of A, come up, come down, go up, go above f of B, come down. So it says nothing about if it's lower or higher. We only care about what's in between. So let's pick an n. So this is an n. It's between f of A and f of B. So we have to draw our n somewhere in this range. It tells us that there's going to be a c in between A and B such that f of c is equal to n. Doesn't tell us that there's more than one. It tells us that there's going to be at least one. Okay, so actually we have three values here. But we're only concerned that there is one. So that's all it says. It doesn't tell us where C is. It just says that there exists a C. So it's an existence theorem. So why does it require continuity? So if we did something like this, and put a jump there, clearly we're not going to find a C where f of c is equal to n because we jump over that value. That's why it must be continuous. Now, why do we have a condition? It does not equal f of b. Well, if we had a and b, and n has to be between f of a and f of b, we're not going to find a value between a and b that equals n. There's no c anywhere in here where f of c equals n. Okay, so that's why we have to have this condition. Okay, let's look at an example. Prove that there is a root of the equation 4x cubed minus 6x squared plus 3x minus 2 equals 3. And the root is between 1 and 2. So what we do is we let f of x equal this left-hand side. We are looking for a c between 1 and 2, such that we say such that a lot when we're doing proofs, so we abbreviate as t. F of c equals 3. Okay, this is our n. Therefore, a equals 1, b equals 2, n equals 3 in the IVT, Intermediate Value Theorem. So we need to show f of 1 equals, and we just substitute it in. 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2 equals -1, and that's less than 3. That's our n. We have to put n in here. F of 2 equals 4 times 2 cubed minus 6 times 2 squared plus 3 times 2 minus 2. And if you do some arithmetic there, you'll find that this is equal to 12. That is greater than 3. Thus, f of 1 is less than 3 is less than f of 2. And we need to say that this is a polynomial. F is a polynomial. Therefore, it is continuous. So, by IVT, there exists, that's a backwards E, and it's there exists, a C between 1 and 2 such that f of c equals 3. Okay, just to reiterate, there's a C between 1 and 2. We don't know what the actual answer is. We just know that it exists. Okay, let's consider this problem. We have, this is actually just D again, and this is E, so I'm repeating this. But if we're looking for n equals 0, and we have f of D and f of E, this does not work. F of D less than n less than f of E. Okay, so n is not greater than f of D. N is not between these two values. If we look at the green part, if we wanted to find a value between A and B for this green one, yes, it'll work. If we're looking for n equals 0, because this is f of A, this is f of B. It doesn't matter that it's going down, we just reverse the signs here, but it works. If we have our A and B here, it also works, because it crosses n equals 0. Our f of A is below 0, our f of B is above 0. So know when your conditions work. So this is just a matter of getting to understand what the theorem is and isn't. And that completes this lesson.